In order to introduce the idea of what I mean by an increasing function and a decreasing function, let us look at the graph of sine of x.
First, we want to understand what we mean by increasing and decreasing. So we're going to let f of x be a function and s be a subset of the domain of f. So we say f is increasing over s if and only if the following condition is met. For any two arbitrary x values in s with x1 less than x2, that means that f of x1 has to be less than or equal to f of x2, and we only consider strictly increasing if it's, strictly less than. Now, if it's decreasing, it's the same thing, except f of x1 is going to be greater than or equal to f of x2, and we'll just say f is monotonic over s if and only if it's either increasing only or decreasing only, but not both. Now, over here I have an example of what I mean. To the left of GF line GF, the function is increasing, right? It's going up as our x values go to the right. But to the right of GF, we have a decreasing function, which is going down to the right of GF. And now we'll bring it back to sine of x.
So watch our blue and red points, right? Right here, when we are going to the left of pi over 2, our function sine of x is increasing because for the point on the left, its output is going to be lower. However, as we go past pi over 2, the function begins decreasing. And this gives us a more geometric understanding of what increasing and decreasing and monotonicity means. And with this understanding, we can relate that all to what the derivative has to say. So notice how when our derivative, which is the slope of the tangent line to the graph, is positive, the function has to be is actually increasing, right? When all of the derivatives in an interval are positive, the function is increasing in that interval. Now we showed already sine is increasing from 0 to pi over 2, and notice how all of our derivatives in there are positive. On the other hand, though, if we have all the derivatives are negative in an interval, then we know that the function has to be decreasing, as we can show by our example to the right of pi over 2. Now, this is very important because we're going to be studying exactly what happens when it is 0, but in order to understand increasing and decreasing as well, we are going to have to use the fact that monotonicity the sign of the derivative implies monotonicity.
So now let us define what we mean by a local or relative maximum and minimum. Now we say C is a local maximum f of x if and only if first C has to be an interior point of the domain, right? And locally at C, f of x is less than or equal to f of C. Also for the case of minimum, f of x is greater than or equal to f of C. Now remember what it means for something to be locally true. That means in an interval around that point, right, containing that point, um, or in a neighborhood, you may say, you may hear delta neighborhood interval containing the point, all the function's outputs are less than or equal to or greater than or equal to the function at C. So graphically, you should be able to identify local maximum and local minimum. Right here we have a local max because at 0, f of 0, we can find an interval, right, where all of the function's outputs are going to be less than f of 0. And over here we have a local minimum because we can find an interval where all of the function's outputs are going to be greater than f of whatever this point is, right?
But now what happens if our to our derivative when we are at a maximum or minimum, right? That's what we care about. So I want you to see how our derivative is going to get closer and closer to 0 as we get closer to the maximum. And in fact, when we are at our maximum exactly, the curve flattens out, right? It's a change in monotonicity, so we're going from increasing to decreasing, meaning that we're expecting our derivative at an extreme to be 0. And can we formalize that and declare a theorem that we can use potentially future on to find maximum and minimum? Well, yes, we can.
So here's our theorem, the zero derivative at local extremum, and it states that if x naught is a local extremum of f of x, and f is differentiable at x naught, right, the derivative is a real number, then the derivative is zero, right, this idea that we were talking about, okay? Basically what our theorem is saying is that at an extreme, either the derivative does not exist or it's zero, right? And we're going to prove it by taking cases. So case one, we're going to assume that x naught is a local maximum. That is our definition. Locally at x naught, f of x is less than or equal to f of x naught. And we're going to assume, toward a contradiction, that it is not zero, right? We want to show that it is zero, so we're going to assume it's not. Now, case 1.a is that we're going to assume it's positive. Now, by the upward trend theorem, which I didn't really talk about, but all you need to know is that it says that um, basically, in easy terms, is that a function, if the derivative is positive, has an upward trend, right? In an interval to the left, we have that all the function's outputs are less, and in an interval to the right, we have that all the function's outputs are greater than the function output at the point, right? So we're going to restate that. For all x in a right delta neighborhood uh, of x naught, f of x has to be greater than f of x naught. It has an upward trend. But since x naught is a local maximum, then f of x naught is greater than or equal to f of x for all x in that delta neighborhood. Thus, locally at x naught plus, f of x has to be greater than f of x naught, which is greater than or equal to f of x. But this means that f of x is greater than f of x, and that's a contradiction. So it can't be positive. Now we're going to assume it's negative, and we're going to do the same thing, but with the downward trend theorem. So we know to the left, f of x is greater than f of x naught. But again, since we said x naught is a local maximum, we know that f of x has to be less than or equal to f of x naught. And I know you see the contradiction now, right? Again, f of x is less than f of x, which is a contradiction. So in any case, we know that the derivative has to be exactly zero. Case 2 is saying that x naught is a local minimum, but all we have to do is consider our new function, negative f of x. Now this means that x naught is going to be a local max, and we can just use the previous case to note that its derivative is zero, meaning that the derivative of just f of x naught is going to be zero, right? So that is our two cases, and by exhaustion, we know in any case, a local extremum, which is differentiable at a point, right, is going to have a derivative that is zero. So to recap, here we have an example of the theorem, right? Locally, at x equals zero, we have a maximum, right, and it's differentiable, so that means that the derivative has to be zero. That's a recap. But is the converse true, right? Well, no, because look at our following counterexample. X cubed flattens out at zero. The derivative is equal to zero, right? But that doesn't mean that it's a local extreme. In fact, it's strictly increasing everywhere. So we know that it doesn't have any local maximum or minimum. The reason why this happens is because we know that in order for a local extreme to happen, we need to confirm a change in monotonicity. The graph has to go from decreasing to increasing or increasing to decreasing. And this is a key concept we're going to use in the first derivative test. So remember, critical points, meaning that where the derivative does not exist or where the derivative is zero, does not mean that those are local maximum or minimum. They're just our candidates for local maximum or local minimum.
Hopefully that review or introduction into the zero derivative at local extremum, what the derivative tells us about monotonicity of a function, and increasing, decreasing, all that really helped you. And if it did, this video did take me actually a surprising long amount of time to animate and to make. So any support obviously would be appreciated. In the next video, I will most likely be discussing the first derivative test and the mean value theorem, Rolle's theorem, all of those up to come. So if you do want to see those, I'll try to make those as soon as possible. Thanks for watching and good luck.